Hello everybody, and welcome back to Lesson 3 in Chapter 4 of the Dynamic Control Assistant Enlisted curriculum. I'm Lieutenant Timothy Mueller, and we'll be going over in this lesson the sign correction for a statical curve of stability. Now, in the first lesson in Chapter 4, we had talked about the statical curve of stability off of an assumed kg, or an assumed center of gravity. Basically, what that told us is from 0 to a wide range of angles, what is that writing arm, that GZ, going to be for that assumed center of gravity and with the center of gravity right on the center line? So basically, it was a little chart that told us this right here, this writing arm for, like I said, that specific, very specific assumed center of gravity. Now, we know that the center of gravity from previous lessons is always going to be changing. You can move weight up and down, you can deballast, you can bring on fuel. There's 1,000 different things that you can do to change that center of gravity. So it's never actually going to be precisely on that point. Now we're going to start talking about how to correct for those changes, those real world changes. And this is a sign correction. So we know that the center of gravity can move vertically, up and down along the center line, and it can also move horizontally, perpendicular to that center line. We're going to start talking about vertical changes now. So we have this right here. We have the ship that's inclined over an angle theta, and it has an original center of gravity here with an original writing arm at this theta right here. We have buoyancy here. This is the line of buoyancy, and the keel over here. This is nothing different than what we saw before with the stability triangle. Now, we had already seen if we raise the center of gravity, or if we decrease that GM, we already saw generally how our writing arm was going to get lower and lower as we get that G closer to M. Now we have to find out exactly how much less does it become. So we have here original writing arm. We have here a writing arm, like a new writing arm based off of a new it might be a displacement or a new condition that the ship is in, where the center of gravity is now higher than the original center of gravity. So it moved from here, G0, to here, G1. How much did our writing arm decrease from here to here? So if you look at it, you know that you have this much originally, this much now. So if you just drop a straight line down, now we split what we originally had into two values. You have this here, which is just the same length as our new writing arm, and then we have this length right here. And let's call this here point P. If we don't know our new writing arm, is there any way that we can solve for this length right here so that we use what we know, GZ, which we get from our statical curve of stability from that kGa, the assumed kg, and then this value that we calculate for in order to find our new writing arm? And we'll see that here in just a second. All right, so we got our stability triangle, and we see that we want to find this, which, as we've said before, is the exact same length as this. We know this already from our statical curve of stability, so now we're trying to find this length right here. So let's take this and just blow it up. Let's kind of zoom in on it. So following over here, we have this triangle here, which is just this triangle here. We have G0, which is the original center of gravity. Then we have G1, which is the new center of gravity that's higher than the G0. Then we have this point P, which is where we draw that straight, or we drew that straight line straight down from the new writing arm to the original writing arm. So this distance here from G0 to P is going to be the reduction in GZ, GZ being the original writing arm, due to the rise in G. And G0 to G1, this length here, is how far G, the center of gravity, moved from G0 to G1. Now, we know what this is, and we also know what this theta is. We know this is the right triangle, so now using trigonometry, we can find this G0P, this reduction in the writing arm, and then once we find out that G0P, then we can subtract that from our original writing arm. So we originally had this. We're going to solve for this using trigonometry, which is this, which is going to give us this value right here, which is the exact same as our writing arm that we have in our new condition. So now, using trigonometry, we will get that this GP being, remember, the reduction in the writing arm, the original writing arm, due to our vertical rise in G. GP equals G0 times G1, which is the hypotenuse here, times the sine of theta. Now we know that the statical curve of stability goes from 0 all the way to, is it 80, 90, 100, it might even go further or it might go a little shallower. This sine theta is going to change in value with each angle that we're at. So we have to look at the inherent behavior of the function of sine and take that information and somehow make it available to us that we can use this information in our statical curve of stability. So a sine function looks just like this. We have, it starts at 0 degrees, then it achieves a maximum at 90 degrees. So sine of theta, just this term right here, equals 0 at 0 degrees. It equals a half at 30 degrees, and then it equals 1 at 90 degrees, right here. So, and then it continues on at 150 degrees, it goes to a 0.5, and then it goes back to 0 at 180 degrees. However, typically with ships, we're only really concerned about 0 to 90. So in this course and in following lessons, even when we go to cosine curves, or I'm sorry, cosine corrections, I'm only going to go from 0 to 90. So if we only really consider this much, so everything this way, we're looking at a function that is pretty much 0 at 0 degrees and still maintains small values through small degrees, but it becomes a maximum at 90 degrees. Taking that information that we know and then plugging it into here and now taking a look, we see that at low theta, so let's say theta equals 0, GP, the reduction in the writing arm, equals however far it moved times 0, which means that there is no reduction in the writing arm at 0 degrees of inclination due to a vertical rise in the center of gravity. And that makes complete sense. If we have a center of gravity that's perfectly on the center line, no matter where it is on that center of gravity, as long as it's below the metacenter, then we're always going to just stay perfectly even keel. There's not going to be any reduction or gain in the writing arm that's going to cause a writing moment to want to make us incline. However, as we start to incline over and over more and more, this sine theta term starts to increase. And it increases very rapidly here in the beginning and then eventually tapers off towards its maximum at 1. When we have a ship that's inclined over 30 degrees, now we have a reduction in the writing arm equal to how far the center of gravity shifted off that kGa, or that initial G0, times 0.5 when we're at 30 degrees. When we're at 90 degrees, we have 1. We have sine of theta equals 1. So GP equals the entirety of how far the center of gravity moved. Now, before going any further, let's kind of take a recap on what we've done so far in this video. So the big takeaway so far is this equation right here. G0 P, which is the reduction in the writing arm at any given theta, right here, equals G0 G1, which is the distance that the center of gravity has moved from its original location at a assumed center of gravity up to its current location, times sine of theta. Sine of theta just being the relationship between this side here and the hypotenuse. We also learned about the behavior of the function sine. We saw that sine equals 0 at 0 degrees. We saw it equals 0.5 or a half at 30 degrees. And we also learned that it equals 1 at 90 degrees. Now, how do we take all this information that kind of doesn't seem to be relevant at all and then put it together at a statical stability curve? Let's do that right now. We have a curve of statical stability right here. Just a standard look for a curve of stability. Nothing too wild or out of place here. The GZ axis goes from 0 to 4. And here we see a range of stability from 0 to 90. 90 being our point of vanishing stability. Now let's apply a sine correction to this. We know that the the amount that our writing arm is reduced is going to change throughout that angle, and it's going to behave just as sine behaves. So we're going to expect a minimum in the reduction at 0 and a maximum at 90. Now in this prompt, we're given that G0, G1 equals 0.6 feet. We're going to learn in the next example problem later in this video, we're going to have a ship that has a certain displacement, and we're going to add weight to it up high, and we're going to see how to calculate how far that center of gravity changes. Then we're going to do this example kind of over again, but in that more specific situation. But for now, we're just given that G0, G1, which is the distance that the center of gravity moves vertically, equals 0.6 feet. And this is going to be up vertically. Now, we just apply this equation and this table here to this. So, let's start off at 0 degrees. We know that at 0 degrees, we will have a writing arm that's reduced by 0.6 because we have essentially two terms here. We have this term, which is always just going to be 0.6 because that's what we were given. And then we also have sine theta. And sine theta is going to change from different degrees. So at 0 degrees, which is right here on the statical curve of stability, 0 degrees, I'm taking 0.6 times 0, which is going to be 0. So I can mark this, make a little point right there. All right, next up is 30 degrees. Now, if you have a calculator or computer software of some sort, you can be much more precise in how you define sine of theta. You can do at 0 degrees, 5 degrees, 10 degrees. But when you're doing one of these curves very, very quickly, in a stressful situation, it's very easy to just memorize this table, and you'll get an answer and a curve of stability final product that's not too far off from what you would get with a computer. So in doing this example and the next example, I'm going to be using just these points and creating a sine curve off of them. So now we go to 30. At 30 degrees, I know that my sine theta is 0.5. So I go back up here. My reduction in writing arm equals G0, G1, which is 0.6, times the sine of theta. At 30 degrees, sine of theta is 0.5. So now I have 0.6 times 0.5, or half of 0.6, which is just going to give me 0.3. So now I go over on this side. I say at 30 degrees, I now have 0.6 times 0.5, which is 0.3. So I'm going to mark 0.3 right above 30 degrees. And that's going to be right around there. Next, using this table, I'm going to move to 90 degrees. 90 degrees, I know that sine equals 1. So now my reduction in writing arm equals G0, G1, which is always going to be that 0.6, which was given to us, or we had calculated for, times sine theta. Sine theta is 1. So now my reduction in writing arm is just 0.6 times 1, or just 0.6. So now I go over here to 90. I try and find 0.6 right here, right around there. Also, and I make a point there. Now, this is my kind of pseudo sine curve, because the sine curve is much more smooth than this. However, this is going to give me just enough information that I need to make a quick and rapid decision. So, in order to finish off this curve, I have to draw a line from the first point to the second point. Then I draw another line from the second point to the third point. Don't try and draw a straight line like that, because you're not going to get the behavior right in this area that you would if you were more precise. So, I'm going to take this right here, straight line from 0 to 30. Then I do another one from 30 to 90. Right there. Now this curve right here is telling me the value of this at every single angle. At 0, I know it's 0. At 50 degrees, it's going to be right around at 0.45, 0.5. 70 is going to be a little bit higher. 80 a little bit higher. 90 is going to be at my maximum at 0.6. Now, that doesn't really tell me anything as a DCA. This tells me something. My writing arm tells me something. Now, G naught, Z naught, so my original writing arm, is already known at every single angle. Do you know where it is? It's right here. It's our statical curve of stability. So this curve here is this. My sine correction curve right here is this. So now, just by looking at it, I can take what I already know here, subtract this, and I'm going to get this. This is the same as this, which is what I'm trying to find. So awesome. Now I have all the information I need in order to redraw this curve, but corrected for a vertical rise in the center of gravity. So how do I do this? I need to find this value. So I can either take my original curve and then subtract my sine correction from it and then redraw from there, or I can just take the value between the two curves and then redraw that point. I'll teach you both here right now. Now let's just start off with taking this value and then subtracting our sine correction from it. So basically you would take something like dividers or maybe a ruler, any way that you can measure a distance on this graph. And I would say at 10 or maybe even 20, you would measure this distance here. If you take dividers, you go right here, and you know that that value that you're measuring is this right here, this G naught P. And I want to subtract that from G naught Z naught, which is my statical curve of stability. So I can take that and, keeping it the same distance, just raise it up directly straight up, and then make a point where they would meet together like that. So I took this distance at 20 degrees, and then I raised it all the way up to the statical curve. This point is now telling me the writing arm that my vessel has at 20 degrees. And you have to do this using your dividers or ruler, whatever you might be, at each individual degree. You don't have to do, 10, 20, 30, 40, 50. You don't have to go by increments of 10. You can go, 20 and then 40 and 50. You can kind of spread them out, but you have to give yourself enough data points so you can draw a smooth curve through all those points. So let's say I do 20, I got there. Now 40, I measure there. Now I take my dividers, go all the way up, right above 40, right there, and I make a mark right about there. If I go back to 10, I don't have as much of a correction to make. So it would go right about here. As I progress from 0 to 90, I'm now subtracting more and more and more from my original curve, because that's just how sine of theta behaves. So if I go to 70, I have this much that I have to remove, take that all the way up here, and make a mark right around there. Now here at 90, I have this much distance from the axis, to the axis being this horizontal axis, to my sine correction. I take that distance and I have to subtract it from my statical curve of stability. Well, my statical curve of stability goes to 0 at 90. So I take that and I actually subtract it from 0. So my point is going to be right around there for 90. Same thing with 80. I go here, subtract it from there, it's going to be right around there. Now I have enough points that I can actually draw a smooth curve through all of them. So let's do that right now. Let's draw this smooth curve and see exactly how this works. Actually, we're going to need another point right near our maximum writing arm. So let's go right here about 55 or so. There you go. That should give us enough information now. Now, we start at 0 again, and we just go right through these points, drawing a smooth curve. There. Now we have done a sine correction to our original assumed kg statical curve of stability. The sine correction is due to a vertical rise in the center of gravity. We know that if we raise the center of gravity, we're going to be losing writing arm. If the center of gravity dropped, the formula is exactly the same. However, you don't subtract from your original writing arm, you would add to it. But being DCAs, we typically are concerned 99% of the time with reductions in writing arm. So that's the rise in G. And in later chapters, we're going to learn about what causes virtual rises in center of gravity. But for now, just think about how far the center of gravity moves, and then how we can correct when we take on, if we take on damage or if we add weight really high. Now, looking at this new curve, if we have this as our original, and then this is sine corrected, what do we see right off the bat? We see that our angle of maximum writing arm has actually moved to the left a little bit. This means that our angle of maximum writing arm has decreased, but also our danger angle has decreased. Also, we see that our range of stability has gone from 0 to 90 to 0 to 87, maybe? Being our point of vanishing stability at 87. However, we still have 0 writing arm at 0. We haven't incurred any bit of a list yet. So this is how you do a generic sine correction onto a curve of statical stability. Let's go into an example problem and see exactly how we calculate this G0, G1, how far the center of gravity moves, if you remember back from previous chapters. Then let's apply this same rule to here. But instead of using the divider approach here, like I did in subtracting, I'm going to use another approach that you can do using dividers, but it'll be a little bit quicker. All right, now for this second example, let's say that we have a ship and we have an original displacement of 1,800 long tons, and we have a kg original of 14 feet. Now let's say we add some weight at a certain height. We're going to add 15 long tons, 60 feet above the keel. We have to find out how far, first off, we have to find out how far our center of gravity has moved from this 14 feet. Then we can start applying our sine corrections, assuming that that weight was added directly on the center line. How do we do that? Well, if you remember back from chapter 2, if we want to find how far the center of gravity moves from one position to another, we just take the added moment from that weight addition, and then we just divide by the total mass of the system altogether. So your G0, G1 is going to be your weight, which is 15 long tons, times 60, which is going to be that location where we put it, then divided by the total displacement of the system, which is going to be the 1,800 long tons plus 15, which is 1,815. Then you do this math, and you get 0.496 feet, or if you just round that up, 0.5 feet, and that's a much easier number to work with. This here is our G0, G1. Now, if we go into this formula, we're trying to find this. We know this now. We just calculated for it. Now we have to apply the sine behavior and then draw a new graph or draw a new chart. So if I can find my marker, here it is. We know that sine theta equals 0 at 0. So we already got our first point right here. Next, we go to 30 degrees. 30 degrees, sine theta equals 0.5. If this here is 0.5 feet, sine theta at 30 degrees is 0.5. All we do is multiply 0.5 by 0.5, and we get 0.25. I've changed up the axis scale here, because this is a different ship. So you have at 30 degrees, I take half of G0, G1, so 0.5 times 0.5 is 0.25. At 30 degrees, I have 0.25. Next, I go to 90, because that's the next thing in my table here. At 90 degrees, sine of theta equals 1. So now I'm taking 0.5, which is what I calculated here, times 1. I know that my G0, G1 is 0.5, so I just take 0.5 times 1, which is 0.5, and I make that point at 90. So it's going to look like it's going to be right around here. Awesome, I got my 3 points. Now I just draw a line from the first one to the second one, then from the second one to the third one. So I go here to here, then I go from here to here. This here is now my sine correction curve. This curve, this curve that I just drew here is the graphical representation through all degrees of inclination of this right here, this GP. Now if I just take my original writing arm, which is my statical curve of stability right here, and I subtract this sine correction, I'm going to get what I need to find, which is going to be my writing arm. Earlier I showed you that if you just take dividers and you go at different degrees, you can make dots underneath like that. The other way, still using dividers, is to just find the distance from the top curve to this sine correction curve, and then take that and then drop it down to the axis. So if I do it that way, 0 is always going to stay 0 because sine of 0 is 0, and these statical curves, assuming the center of gravity is on the center line, is going to be 0. Let's go for 20. I take my dividers and go right here, so I have this distance in between the two. If we think like this, I'm now putting my dividers on this value right here. However, it's not giving me the direct measurement of it. I have to drop it down and kind of anchor it at 0 so that I can actually read off of this axis what that value is. So let's take our dividers here, drop it down. Now I'm going to get a point right here. Now, when you come to this school, I expect you to be a little bit more precise than using your fingers. However, you're going to be given dividers or a ruler so you can make a more precise dot. Now, say here, I have this, say at 40, I now have this distance here. So I drop down, I'm going to get a point right around here. And now, since I'm just using my hand's not nearly big enough for up here near the maximum writing arm, but at 60, let's get an approximation right about there. 50. Be right around here. 70, we go here. Be there. 80 is right here. Now I have to drop it way down here. Now here, my original curve of statical stability had a point of vanishing stability right around 86, 85, 86 right there. So now I have to take that distance between the curves and drop it all the way down to the axis again. So I take, let's go here, and let's drop that down, giving me this right here. And then anything beyond that, we really don't need. So my curve of statical stability ends here at around 85, but my sine correction curve goes all the way to 90. I don't really need that sine correction curve past my point of vanishing stability. Excellent. Now I have dots that represent my sine corrected curve of stability from 0 all the way out to my point of vanishing stability. Now all I do is just draw a smooth curve through them all. So starting here, there's 20 there. And just like that. Again, we see that our point of maximum, or our angle of maximum writing arm, shifts a little bit to the left, as does our point of vanishing stability. It goes from about 85, 86 to about 82, 83. We see that from 0 all the way to our point of vanishing stability, our writing arm has decreased, which we would expect. We know that if we make something more top-heavy, if we decrease our GM by increasing our center of gravity, then we're always going to have these reductions in writing arm, no matter what theta we have, or what angle of inclination we're at. So we would expect that every value along our sine-corrected curve to be lower than our original curve of statical stability. And we see that right here. All right, so in this video, we learned how to perform a sine correction onto a vessel that has a center of gravity that's still along the center line. However, it's not necessarily at that assumed center of location that the naval architect had. We saw how the stability triangle can be graphically represented as this right here. Then we saw how to correct it. The biggest takeaways from this lesson is probably going to be exactly how the righting arm is reduced due to the behavior of sine theta. This sine has a minimum at 0 degrees, and then a maximum of 1 at 90 degrees. Just always think of the stability triangle. You drop a line down to this P. You're trying to find this. You already know this. You've already been given this by your naval architect. You use this equation to find this piece. Then you just subtract them. You subtract them by either measuring those distances or using dividers. Take that, subtract it from there, you get a point. There, subtract it from here, you get a point. In the next video, we are going to talk about cosine corrections. Sine corrections are for vertical shifts. Cosine corrections are going to be for horizontal shifts. We're going to basically be going through the same form of video, but we're going to see exactly how the stability triangle is going to change with a horizontal shift in the center of gravity. But that's going to be for the next video. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.